In this video, we're going to be looking at reflection, refraction and seismic waves, and this is video number 2 of 4 for our waves topic. So let's crack on. Waves can be reflected at a boundary between two different materials. This means when a wave is incoming onto an object, it may change its direction and come back the way it came, or reflect over an angle. Let's look at this diagram of the reflection of waves. What do you notice about these rays of light and their reflection? They always bounce back at the same angle. The angle of incidence, labelled I here, is always equal to the angle of reflection, labelled R, where this green line is just the normal. The normal is a line which intersects the material boundary at 90 degrees. It is important that you remember that the angle of incidence is equal to the angle of reflection. When a wave hits a boundary between materials or mediums, then the wave may reflect. When it reflects, its angle measured from the normal is equal on both sides, or in other words, the angle of incidence is equal to the angle of reflection. As well as reflecting at a material boundary, waves could be absorbed or transmitted. But what does this mean? Well, let's have a look at this block of wood, for example. Here, the waves which are incoming from the left are being absorbed by the wood. The energy which was in the form of waves is now being converted into heat energy within this block of wood. And let's have a look at a cloud of gas. Here, the waves are being transmitted by the gas. The gas is allowing the wave to continue through. There is no change in energy here. The wave energy is still wave energy. And you need to know about absorption and transmission. So as seen with the block of wood, waves may be absorbed at a medium boundary. If this is the case, then the wave in question will stop being a wave and not pass through. Instead, it will lose its energy, and the energy will be converted into another form of energy, like heat, for example. This is actually what happens in a microwave oven. And as seen with the gas, waves may be transmitted and allowed to travel through. The transmitted wave may have different properties to the original wave though. So you should be able to construct ray diagrams showing reflection. And the first step to doing this is to get a pencil and draw the normal to the surface. This is where the incident ray hits the boundary. Use a protractor or set square. It has to be done at 90 degrees to the surface. Step number 2. Now you need to measure your angle of incidence. Use a protractor to do this. So we can see here that the angle is 51 degrees, and that's because the normal is at 90 degrees and the incidence ray is at 141 degrees, and the difference between 141 and 90 is 51. Next, we need to draw our angle of reflection using the protractor again. So to do this, we'll just go the same angle, but on the other side. And finally, we draw in our ray of reflection. And once you've done that, you're done. I should equal R if you've done it correctly. You can always check this with your protractor. So you should be able to explain the effects of reflection, absorption and transmission now. So what does reflection mean? Is reflection where the wave continues into the next medium? Is reflection where the wave bounces back? Or is the reflection where the wave changes into different forms of energy? Well, I think reflection is where the wave bounces back. What is transmission? Is transmission where the wave continues into the next medium? Where the wave bounces back? Or where the wave changes into different forms of energy? Well, I think transmission is where the wave continues into the next medium. And that means that absorption must be where the wave changes into different forms of energy. Let's have a look to see if we're right. Excellent. To investigate reflection, we need to use a protractor, a mirror, a light box and a slit to produce a ray of light. If we use a mirror, then the mirror will reflect the image and make it appear as if the light is behind the mirror. This is how a mirror works. If you remove this cake and place a light source where a light ray travels along these arrows and then hits the mirror, it will reflect with the same angle of reflection as the angle of incidence. And if you look down the rays of light, it will appear as if the light is behind the mirror, when in reality it's on the same side of the mirror as you. When light is reflected at a boundary, the way it behaves depends on the surface which it bounces off of. You may get specular reflection, which is where all of the rays reflect and go one way, or you could get diffuse reflection, and this is where the rays reflect and all go in different ways. Specular reflection happens on smoother surfaces. Water surface is a good example. Rays all hit the water at the same level and angle, so the rays reflect all in the same direction. Diffuse reflection occurs where the surface is more rough. Rays hit the surface and scatter as the surface is at different levels and different angles. A carpet or wooden surface would be places where diffuse reflection, would be found, would be found. So you can see here, where you have specular reflection, you have all the light rays coming in and going out with the same angle. And on the right, where you have diffuse reflection, you can see the light rays coming in and then scattering all with different angles. As well as reflection, you need to know about refraction. Refraction is the bending of light when passing from one medium to another. Denser mediums are more difficult to travel through. Waves slow down when they enter a more dense material. They accelerate when they enter a lighter medium. As they change speed, they change direction slightly. So let's have a look at this picture here. We'll have a ray of light incoming from the left. It enters this block of glass or perspex or whatever it is, and it bends slightly. And then on its way out, it bends to travel in the same direction as what it was originally. It is important to note though that refraction only occurs if the angle of incidence is not zero. If the angle of incidence is zero, then no refraction occurs. Instead, this would happen. The light ray would travel straight through. The angle of refraction is the angle between the normal and the refracted ray. So if you zoomed into that picture of the glass block, you would be able to see that you would have the angle of incidence, which we already know about, and then we would have this angle here, which is between the normal and the ray of refraction, or the refracted ray. And this angle here is called the angle of refraction, and we can measure that. To investigate refraction, you should use paper, a glass or plastic block, and a ray box with a slit, as well as a protractor. And to do this, you start with placing a piece of paper on the desk. You should then get your block of glass and place it parallel with the sides of the paper on top of the paper. Once you have the block of glass on the paper, you need to draw around it. Then, lift the block and pick a point near the centre of one of the longer sides and mark it with a line. It's important that this line is drawn at 90 degrees to the line drawn to represent the side of the block. To help get this right, use a protractor. This is going to act as our normal. Now, you should place the ray box and slit at an angle to the block. Turn on the ray box, but be careful as the bulb can be hot. Turn off the lights in the room at this stage. Our next step is to make sure the ray of light passes through the point where your normal crosses the boundary of the glass. Mark the incoming ray with crosses. Next, you need to mark the reflected ray and the transmitted ray with crosses. And then you need to remove the glass block, draw in the normal for the transmitted ray, and then draw in the lines, including a line going through where the block was, connecting the incidence ray with the transmitted ray. And finally, we need to measure the angles of incidence, that is the angle between the incoming ray and the normal, and measure the angle of reflection, which is the angle between the normal and the reflected ray. And once you've done this, you need to measure the angle of refraction. This is the angle between the normal and the line connecting the incidence ray to the transmitted ray. And once you've done that, you should end up with 3 angles measured: the angle of incidence, the angle of reflection, and the angle of refraction. The angle of incidence should be equal to the angle of reflection, but the angle of refraction should be different. If you're following along in your revision workbook, pause the video now and complete task number 4. And please note that there is more than 1 page of work to do for this task. Next, we're going to be looking at sound waves. Sound waves travel through the air. Particles vibrate and cause other particles to vibrate nearby. These vibrations are like chain reactions. When one particle oscillates, it causes the next one to oscillate and then continues through the medium. Sound waves also travel through solids. When sound waves hit solids, it causes the objects to actually vibrate. However, the process of sound waves hitting solids and making them vibrate is limited to within a certain frequency threshold. Humans can only hear frequencies between 20 Hz and 20,000 Hz. Anything below this frequency we can't hear. Anything above this, where sound is known as ultrasound, we cannot hear either. As you get older, you can't hear higher frequencies, and that's because your hearing tolerance, or the maximum frequency that your ears can detect, becomes lower. Waves in the air convert to vibrations in solids. One example of this is a microphone. A microphone uses a paper cone which vibrates when the pulsations of sound hit it. This is an example of the conversion. It is also true the other way. Vibrating objects cause sound waves. When an item oscillates, it moves around, compressing air particles. This causes a sound wave to form. And a speaker is a solid vibrating, so it's a perfect example to show this. Particles around the speaker oscillate and form a sound wave. So when the solid part of a speaker vibrates, then the air around it has a sound wave in it, as seen by this little diagram here. The eardrum is another example of something which converts sound waves in the air into vibrations in solids. The eardrum vibrates when sound waves are present on it. The eardrum then pushes bones within your ear, which sends signals to your brain to give you the sensation of sound. When sound enters a different medium, the speed of the sound is often changed. For example, sound travels much quicker in a solid than in a gas. But when the speed changes, the wavelength also changes. Wave speed and wavelength are related through the wave equation, which we've already seen before, where wave speed is equal to the frequency times wavelength. When wave speed increases, wavelength increases. If you're following along in your revision workbook, pause the video now and complete task number 5. Next, we're going to look at how waves can be used for exploring. Exploration of things that we cannot see has long been an issue for scientists, doctors, and for people wondering how the Earth is structured. Thankfully, we have developed ways to study below the surface of the skin, the Earth, and behind chemicals even, all with technology to do with waves and their reflection, absorption, and changing velocities. Remember, waves, when passing from one medium to another, can partially reflect. The wave may transmit into the next medium, but also reflect a little bit as well, causing an echo to return in the same direction as where the waves came from. Ultrasound waves have a high frequency, much higher than the upper limit of hearing for humans. Ultrasound waves are partially reflected when they meet a boundary between two different media. The time taken for the reflections to reach a detector can be used to determine how far away such a boundary is. This allows ultrasound waves to be used for both medical and industrial imaging. So what does this mean in practice? Well, ultrasound is used in medical imaging. When you go for a baby scan, sound waves above 20,000 Hz in frequency are fired into the womb, and when they hit the baby, they are partially reflected and come back to a sensor showing an image of how far the waves have travelled since they've been reflected. The end result of this is a picture showing an image, in this case a baby. It is not only babies. Ultrasound can also be used to look at flesh and soft tissue. This is a machine which uses ultrasound. This picture here. Where there is a solid, like a cyst for example, the waves partially reflect and the detector picks the echo back up and constructs a picture for the doctor to look at. Ultrasound can also be used in ships. Echolocation and sonar is an example of ultrasound. Ships can fire ultrasound towards the sea floor. A computer starts a timer and says how long it is until the ultrasound waves get back to the ship. This is the echo from where it bounces back off the sea floor. Once the echo is received, the timer is stopped, and using the speed of sound it can calculate the distance. The speed of ultrasound in water is 1,500 meters per second. If it takes 0.4 seconds for ultrasound to leave the ship and for the echo to get back, then how deep is the sea? Well, we know that speed is equal to distance over time. So we can rearrange this to get distance as speed times time. That means the total distance travelled is 1,500, because it's 1,500 meters per second, times 0.4, because it's 0.4 seconds. That means the total distance travelled is 600 meters. But this is the distance from the ship to the floor, and then from the floor back to the ship. So the seabed, in reality, is only half of this calculated distance. So 600 meters divided by 2 is 300 meters. So the distance between the ship and the seafloor is 300 meters at that point. We're now going to have a look at seismic waves. Seismic waves are waves which are the release of energy after an earthquake. There are two types of seismic waves which you need to know about. There are P waves, or primary waves, and these are the waves which come first after an earthquake. And there are S waves, or secondary waves, and these are the waves which come second after an earthquake. Seismic waves are interesting. This is because P waves are longitudinal waves. This means they have compressions and rarefactions, and if you don't know about that, you can have a look at the first video again. The oscillations are parallel to the direction of energy transfer. But what is interesting is P waves can travel through solids and liquids. S waves are transverse waves. Now, S waves have oscillations perpendicular to the direction of energy transfer. But what is interesting is S waves cannot travel through liquids, and that's because they are transverse waves. A seismometer is a piece of equipment which picks up seismic waves and stores data in a computer. When waves pass through the ground, the shaking is recorded on a computer. What's interesting is seismometers all around the world pick up waves from quakes from the other side of the world. That means waves must travel through the earth for them to be picked up on the other side. Obviously, there is some lag from when the earthquake happens. If an earthquake occurred in Australia, it would be some time before they were being picked up in America or the UK. This is due to waves taking time to travel, because waves have a wave speed. Some places get data more quickly though, which suggests that there are different medium within the earth for the waves to travel through. Remember, P waves and S waves have different mediums which they can and can't travel through. But perhaps the most interesting phenomenon is that seismometers pick up all P waves from earthquakes, but not all seismometers pick up S waves. Why could this be? Well, remember, S waves cannot travel through liquids, so there maybe is some sort of liquid in the way, and seismometers on the other side of the world can't pick up any signals if there are liquids in the way. And that is exactly the case. The outer core is a liquid, and S waves can't pass through liquids. So there are shadows on the other side of the world where these S waves simply cannot be picked up by seismometers. And this little diagram here shows you exactly what I mean. If there's an earthquake in this place here, in Kola it's called, then you can see here on the right where the P waves and where the S waves travel. So you can see these waves marked with a blue line here don't travel through the outer core, which must mean that the blue waves are the S waves, because S waves are transverse and can't travel through liquids. Seismic waves produce evidence about the Earth's structure. The beauty of science is illustrated here. Evidence leads to a conclusion. Seismic waves, a simple phenomenon, shows us that the Earth has layers. They also allow us to estimate the size of different parts of the Earth as well, not just the location. If you're following along in your revision workbook, it's now time to do task number 6.
Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backroadtutoring.com.